In a previous presentation, we saw that the forced response vibration of the system can be expressed as a linear combination of the system's modes. In this presentation, we will continue and develop this expression a bit further. We want to reach an expression which clearly and explicitly shows how the frequency response function, or system transfer function, depends on the mode parameters of the system. This expression we will use later on when we wish to identify the system. The key concepts we will touch upon in this presentation is, well, as before, vibration mode, system pole, mode shape, mode parameters, frequency response function, and the new concept for this presentation, system identification. What do we mean with the system identification? First of all, from a previous presentation, we know that any vibration of the system can be expressed as a linear combination of modes. And we also know that a system's modal model is defined by the mode shape matrix and the eigenvalue matrix of the system. The mode shape matrix is composed by a matrix with the eigenvectors or mode shape vectors as columns, like this. And the eigenvalue matrix is simply a matrix with the eigenvalues as diagonal elements. So, how can we then express the modal solution in terms of physical coordinates? Well, we can transform our solution, our forced vibration solution, back to physical coordinates. That is how we can do it. So, in physical coordinates x, displacement x, we can use the mode shape matrix and multiply with the modal amplitude vector c. And this will then be a linear, as we see here, a linear combination of the mode shapes, where the modal amplitudes determine how strong the contribution of each mode is. So this is, as we have concluded before, that any forced vibration can be expressed as a linear combination of the modes, of the system's modes. From a previous presentation, we also know that the modal amplitude can be expressed like this. Q here is the nth component of the modal force. Mu n is the nth modal mass. And S square n here is the eigenvalue of the nth mode. So if we look upon the displacement component xk, we can, if we insert psi n as this, we can write the kth component like this. And as you can see, as we have seen before, it's a sum of contributions from the n modes. Now we continue this expansion and insert the ordinary force in physical coordinates instead of the modal coordinates. We can achieve this formula. So Q here is the mode shape vector multiplied with the force, exciting force in physical coordinates. So, when we use this, we can actually identify the system's transfer function, because the system transfer function, from definition, is the ratio of the response, in this case the displacement, over the excitation, in this case the force. So this ratio then clearly from this expression is this sum of modal contributions. So you can see here that the system transfer function contains parameters such as this Laplace variable s, the eigenvalue Sn square, and mode shapes and the modal mass. If we can simplify this further by using the so-called mass normalized mode shapes, phi. So if we introduce the mass normalized mode shapes phi kn as the previous mode shape components over the square root of the modal mass, then we can sort of include the modal mass within the mass normalized mode shape components. So this is one of the standard formulations for the system transfer function in terms of the mode parameters, the mode shape vector components and the eigenvalues. More explicitly, we can write for a finite degree of freedom system, say with capital N degrees of freedom, we can express the sum like this. And this is then, of course, the contribution from the first mode to the Kp matrix element of the system transfer function matrix. In a similar way, you can find the frequency response function, which also is a modal, a sum of modal contributions. So by replacing the Laplace variable with I omega, where omega is the angular frequency, we find this expression for the frequency response function element Kp. If we take a 3 degree of freedom example and plot the contribution from the first mode, in this case with the resonance frequency at approximately 5 Hz. And then we have two other contributions with resonance frequencies at 8 and 10 Hz. So the total frequency response function in this case is the sum of all these contributions, and we get the blue solid curve here. And as you can see, close to a resonance frequency, the mode with which resonates at that particular frequency will dominate the total frequency response function. So in this region, the mode with the resonance frequency is 5 Hz will dominate, and that in this frequency region, the mode with resonance frequency at 8 Hz will be dominant. And in between, of course, we have significant contributions from all three modes. So what this figure shows then is that in principle we have contributions from all three modes at all frequencies, but in some frequency regions one or possibly two of the modes may be dominant over the rest of the modes. Now, when we turn to experimental modal analysis, then we must be clear over that one of the purpose of experimental modal analysis is to find a modal model from the measured system properties. And the measured system properties we talk about here is normally frequency response functions. To find this, the process to find this modal model from the measured system property is called system identification. So the basic idea of experimental modal analysis is in fact to first measure a suitable set of frequency response function. Suitable here means that you should select observation points and the frequency region that is suitable for your application. Secondly, with the measured frequency response function, you should determine system mode parameters that fits the measured frequency response function as closely as possible. That is normally done with numerical methods. And thirdly, of course, when you have your modal model, then you are ready to use this model in some way to find, to identify a problem maybe, what causes resonant vibration, for instance, or some other useful application of the model.